last class we have discussed that optimality condition for a function of two variable case. Just we will recap these things. What is this one? We have a function which is a function of two variables, and x star, x 1 star, x 2 star are the optimal point. Around this optimal point, we have given a perturbation with x 1 will perturb by epsilon 1, x 2 perturb by epsilon 2. That perturbation is very small. So, this if you do the Taylor series expansion, we have shown that seen that this the function value at the optimal point, and this is the Taylor series expansion first order terms and second order terms, and the higher order terms, all other higher order terms are denoted by capital R. Agree? This R is sufficiently small compared to the preceding terms when the perturbation is near around very close to the x 1 star and x 2 star. And if you do the and if you bring it this in the right hand side, left hand side, this is the change in function value. From the optimum point, we have given a perturbation, and what is the change in function value? That change in function value is nothing but a gradient of that function multiplied by that perturbation vector. And if you look at this expression, we can see that this term we cannot say whether this is a scalar term, but we cannot say anything about the whether it will be positive or negative, because epsilon can be positive and negative, epsilon 1, epsilon 2. So, this term we have assigned to 0, and it is the necessary condition for this one, and remaining terms is that one, that what is a quadratic term. This we can easily write it into quadratic form. These three terms we can write it in quadratic form, and which we have written like this way. If you see this, we have written this term is assigned to 0 and this is half. This we can say it is a epsilon transpose. Epsilon is a vector which components are epsilon 1, epsilon 2. Then this is the Hessian matrix, second derivative of the functions. Evaluate at x 1 is equal to x star, x 2 is equal to x star, x 2 is equal to x 2 star. Then this is the your quadratic form, and ultimately this is nothing but a, you can write it, this is nothing but a gradient. This is the what is called Hessian matrix. In the second gradient, you can write gradient of a vector f of x, gradient of a second derivative of this function. Agree? So, f of this and evaluate this value x 1 is equal to x star and x 2 is equal to x 2 star, and this we can consider this can be neglected, that one. So, this function value will be positive, because we have assumed that x 1 star x 2 star is the optimal point. So, this function value, if it is a positive, this positive indicates that the point x 1 star x 2 star is a optimal point in other side of these perturbations. Optimal point we got it, that means function has reached to its optimal value. So, this we can say, if we consider this, if we consider h is equal to del square f of x evaluated at x is equal to x 1 is equal to x 1 star and x 2 is equal to x 2 star, and depending upon the matrix value at this h, if h is a positive definite matrix, then we can say that 1 by 2 factorial 2 epsilon transpose into h. That means, we can write it this, that epsilon this equal to f of x 1 star plus epsilon comma x 2 star plus epsilon 2 minus this f of x 1 star comma x 2 star. This will be less than, if we write it, if this value is greater than 0, this indicates this will be greater than 0 provided h is greater than 0, means h is positive definite matrix, where h is nothing but the derivative of the gradient or Hessian matrix evaluate at x is equal to x 1 star and x 2 is equal to x 2 star. If this value is positive definite matrix, this indicates that function value we have reached to the minimum value of this function. If then f again f x 1 star plus epsilon 1 plus x 2 star plus epsilon 2 minus x 1 star x 2 star, this agree. If it is less than 0, if this is the less than 0, this indicates this will be less than 0 provided H is negative definite matrix. Agree? This indicates we got the what is called maximum value of the function at x is equal to x star, means x 1 is equal to x 1 star and x 2 is x 2 star. This is the maximum value, and this condition is for minimum value of the function. Value of f x, maximum value of f x. So, now we can restate our problem, that what is called the necessary and sufficient condition, like this way, that theorem, the necessary and sufficient condition the theorem, the necessary and sufficient condition for function to be sufficient conditions for local minimum or maximum is like this way. Our necessary condition is like this way. Necessary condition, first assign the gradient of this vector, that is what is called gradient of this vector del f of del x with respect to x, you assign this is equal to 0. This is the what necessary condition, where x is equal to, in general now we write it dimension in n cross 1, which is x 1 x 2 dot dot x n. Okay. So, then sufficient condition is our Hessian matrix, that H that is equal to del f square del x x x is equal to x 1 x star. Agree? If sufficient, if this quantity is greater than 0, means positive definite, then function has reached is minimum value. The function has the minimum value at x is equal to x star. You can put it here, that put at x to x star, we are finding out this. Similarly, if h is less than 0, means negative definite, this is negative definite, this implies the function value is obtained at x is equal to x star is the minimum value, sorry, maximum value. For some function value is maximum, at x is equal to x star. So, this is the necessary and sufficient condition for a function of n variables, x is equal to dimension n cross 1. So, this is the necessary and sufficient condition for this one. So, let us take one simple example. Quickly we just take this example. Suppose you are asked to find out the optimum value of this function, optimum value of the function. Either it is a minimum or maximum value of the function. So, the function is given f of x, which is in our example it is a 2 by 2, means it is a function of x 1 and x 2, that is x 1 square plus 4 x 1 x 2 plus 4 x 2 square minus 4 x 1 plus 2 x 2 plus 16. So, our necessary condition, according to the theorem we proved, necessary condition means gradient of f of x is equal to 0. What is the gradient of this one? Del f del x 1 del x 1 and del f del x 2, this is the gradient of this is equal to 0. So, if we differentiate this with respect to x 1, it is coming 2 x 1 plus 4 x 2 minus 4 this, and if you differentiate the second part f with respect to x 2, then it will be 4 x 1 plus 8 x 2 plus 2 is equal to 0 and 0. Solving this set of equation, two equation, algebraic equation, if we solving the equations, we get the stationary points, or we get the stationary point x 1 is equal to 2.5, let us call, we consider x 1 star, x 2 is equal to minus 1.5. That is good to be. Now, we have to see whether the Hessian matrix value of this one, whether it is a positive definite matrix or negative definite matrix or negative semi definite matrix or positive semi definite matrix. So, if you find out the value of the Hessian matrix, okay. So, this is the necessary condition we got, the stationary point here. At this point the function may be minimum, maximum, positive semi definite, negative semi definite, all these things. So, we have to further check with the sufficient conditions. Sufficient condition. Okay. So, whatever the Hessian matrix or the differentiate the gradient of a vector, gradient of the function, gradient with respect to x once again, or this is the Hessian matrix. You find out the value x is equal to x star. Differentiate the gradient once again with respect to x, which is nothing but a Hessian matrix. This value you find out. If you find out this value, we have already see this one. Now, what is our Hessian matrix? If you see this one, this is nothing but a del square f of x del x 1 square del square f of x. This is already we have written so many times. So, just without explaining in details, I am writing the expression for the Hessian matrix. So, this value you evaluate x is equal to x star, and our case x 1 is equal to, if you see, this is nothing but a or x 1 is equal to x 1 star, which we got it 2.5, x 2 is equal to x 2 star, we got minus 1.5. So, put these values in this one, and in these values are, if you see this, if you differentiate already we have differentiated in the gradient of a function we have find out you are going you differentiate this with respect to x 1, again you differentiation this with respect to x 2. So, this is a if you differentiate this one that is x 2 agree, this is missing that subscript, this is the x 2. So, if you do this one and put this limit, it will come 4, 4, 4 and 8, and let us call this matrix is our H. Now, you check it whether this is a positive definite matrix or not. Since the diagonal elements are all positive, so you can proceed for the positive definite matrix first. So, leading principal minors, as you know, the leading principal minor of order 1 is 4, which is greater than 0, is 4 which is greater than 0. Leading principal minor of order 2 is matrix itself, the way we are calculating leading principal minors. That means, determinant is determinant of 4, 4, 4, 8, the determinant of this one, which is equal to 32 minus 16 will be 16, which is greater than 0. Therefore, our H is positive definite matrix, implies what? That function is attained is minimum value at x 1 is equal to x 1 star means 2.5 and x 2 is equal to x 2 star 1.5. At this point, the function value attained is minimum value of the function, since this is a positive definite function, positive definite matrix. So, we know at this moment that our conclusion is now f of x has a minimum value, minimum value at x is equal to x star, which is equal to 2.5 minus 1.5 at this point. And its value is, if you put this value in that expression, f of expression, the value of the function, you will get f of x at x is equal to x star means is equal to 2.5 minus 1.5. This is the stationary point, we got it if you see earlier. So, that value we will get 9.5, please check it. Okay. So, we know at this moment how to find out the a function which is a more than one variables or multivariable functions of dimension n, how to find out its local optimum and local optimum means local minimum and local maximum value of the function. So, before we proceed further, first we see that what is called that if you have a quadratic form is there, if quadratic form let us call x transpose p x, it is a n variables are there, this matrix immediately the dimension is n cross n and this is a scalar form. So, if you differentiate and this is scalar is a function of n variables x 1 x 2 dot dot x n. So, if you differentiate this one with respect to x, that differential, let us call this I am denoting by f of x is equal to that one. So, if you differentiate this a scalar function with respect to a vector x, the results you know this is nothing but a del f of x del x 1, similarly del f of x del x 2 dot dot del f of x del x n. So, the results you can easily verify it writing the details expression of this one and expand it, write the polynomial quadratic form with x in terms of x 1 x 2 and p assume a matrix of n by n matrix, agree, with a assume that p is a symmetric matrix, then only p is a symmetric matrix. agree, then results is p into twice p into x, agree, and dimension is that, assuming that P is a symmetric matrix. So, this you expand it in terms of x 1 x 2, just product it, and P elements you consider the P 1 1, P 1 2 dot dot P 1 n, and the second row elements are P 2 1, in place of P 2 1 you write P 1 2, because this is a symmetric matrix. Then differentiate each element, each f of x in terms of x 1 x 2, ultimately the results will come this one. So, this is a quadratic form where P is a symmetric matrix. If you differentiate that function with respect to it, the results is 2 p x. Next is the derivative of linear function. This is the quadratic function. The derivative of linear function. F of x is equal to a 1 x 1, a 2 x 2 plus dot dot a n x n, and this is called linear function. Even there may be a constant term c. So, when c term is there, constant term, we call it is a affine function. We will come details in later. So, let us call for the time being this is. So, you differentiate this thing with respect to x, then what is the results? That straight away you can find out that f of x is a scalar function, but which is a linear. Now, you differentiate with respect to x vector. So, that gradient of that x you are finding out. Again, if you do this one, I am not writing that expression, you know that the gradient of function, each element you know how to do this. This will come a cross n. So, what is a n? This expression, if you see this expression, I can write into row vector and column vector form, dot dot a n, agree, this is row vector multiplied by x 1 x 2 dot dot x n, which I can write it is equal to A transpose x, x is a n cross 1, and A is where A is, I can write it where A is is equal to your A 1 A 2 dot dot A n, whose dimension is n cross 1. So, in short, now I can take, if you have a linear function is there, if you differentiate with respect to x, x is a vector x 1 x 2 this, then results is nothing but a, that means function which is expressed A transpose x, the inner product of two vectors, this A transpose x, agree. If you differentiate with respect to x, then results will be not A transpose, it will be A, and that you can easily verify this one. So, keeping these two results in mind, then we can what is called proceed further, that unconstrained optimization problem. At the beginning of the class, I think like first lecture we have discussed what do you mean by the constrained optimization problem, unconstrained optimization problem. That means objective function is given and there is no constraint subject to any conditions, or and as well as there is no side constraints are there. So, this is called unconstrained optimization problems. So, you are now discussing is a unconstrained optimization problems. But using some numerical techniques, But the numerical techniques is say it is a iterative process, iterative. The objective of iterative process is like this way: you guess some value of x, then find out the function value f of x. With our problem is minimization of a function. So, you take a initial value of a that variable x, let us call x superscript of 0, you take this one, and now next iteration next iteration you got the improved value of x, where x is a n variables, and if the function value is improving, means if our problem is minimization, the function value is decreasing, that means slowly we are each iteration we are going to approach to minimum value of the functions. So, our iterative process, you can see iterative process is nothing but the objective of iterative process iterative optimization process, iterative optimizations. Process is to reach a minimum value of the function, minimum value of the function, minimum value, or you can write minimum value for the cost function or objective function f of x, which is n variables. Agree? Suppose that at kth iteration we have not reached to the minimum value of the function. Agree? Next, k plus 1th iteration of our value, that k plus 1th iteration, the function value, if it is it should decrease it. Agree? Then we are saying that we are approaching to slowly, if it is each iteration value is decreasing from the previous iteration value, that means we are approaching to the our minimum point, minimum value of the functions. So, mathematically we can just write it here, f of x, f superscript f, superscript indicates the iterative kth iteration, the value of the function, kth iteration the value of the variable, not function, value of the variable, and when you put f x of k, it indicates that function value at kth iteration. So, x superscript k indicates the value of the decision variable at kth instant. If you put the values of x in the function expression, then you will get the value of the function at kth iterations, value of the function. So, if we assume at kth iteration the function has not reached to the optimum value, then k plus 1th iteration the function value will be less than this, because we are approaching to the minimum value. So, we can write it at k plus 1th iteration value is less than this value. So, I can now write it, what is k plus 1th iteration value? It is the value from kth iteration value plus some perturbation about kth iteration values, kth iteration, the decision variable at kth iteration, what is this variable, from there is the perturbations. Let us call that perturbation, I will writing is del k lambda k dk, which I am writing delta x. So, this value, and at kth iteration the decision variable value is x to the power of k, and function value is this one. At k plus 1th iteration, that means at kth iteration what is the value of decision variable value, from there is a some perturbation is delta x, and that at that value, at that what is called iteration, what is the function value f of this one, and that value if it is less than this quantity, that means we are approaching towards the minimum point, each iteration should decrease its value. So, lambda is a scalar quantity whose values is greater than 0, agree, and dk, naturally you can f the x superscript k, that decision variable I am adding with another vector, where lambda k is scalar quantity, dk must be vector. So, that decay is called the search direction vector, meaning we are looking for, that means from kth iteration the decision variable x k, from there we are moving in such a direction such that the function value is decreased at k plus 1th iteration, function value should decrease, and we have to move in such a direction, and that direction I am denoted by decay. Okay. So, if you do this one Taylor series expansion, because I told you that delta x is the perturbation from the kth iteration, the decision variable value at kth iteration, from there is a perturbation is delta x. Okay. So, if you do the Taylor series expansion up to first order, then we will see f of x of k this plus gradient of that vector f transpose of x k and put the value x is equal to x superscript kth iteration value, because I am doing the Taylor series expansion around this point where kth iteration decision variable values, from there into delta k lambda k into dk. So, that another what is called higher order terms are there, I have neglected, because I am considering that delta x is very small, considering that one, and that value if it is less than this one, then we are approaching in the right direction. So, that function value each iteration, when iteration from k to k plus 1th iteration, the function value is decreasing. So, this now you bring it in this side, this equation, if you bring it this one, this function x of superscript k minus f of superscript of k, this plus gradient of this function of f of x at x is equal to x superscript k into lambda k dk must be less than 0, because this part I have taken here, this and this cancel. So, this quantity should be less than 0. This is a scalar quantity. See, this is a means row vector. Lambda is a scalar quantity whose value is greater than 0, mean positive quantity, and dk is a vector, and that vector is a column vector. So, you have to select dk in such a way that product, because lambda k is a positive quantity. So, it will not affect that value of what is this quantity less than 0, it will not affect. So, we can write therefore, gradient of this one f of x, x is equal to x superscript of k into dk must be less than 0, negative quantity. So, there is a lot of different choices of decay is there, may exist. One of the choices is obvious, that it will be a negative quantity, that this product will be negative quantity when we select or choose that decay value is equal to minus that f of this value. Again, when decay value, if you select that value, it will be a that gradient transpose into that gradient with precedent. So, this product, this into this, okay, or you have to write it x equal to x k. So, this into this is a norm of vectors, and that is always norm means distance of the vector, and distance is a positive quantity and preceded with a minus. So, if I put it here this choice, then it will coming like this way. See, del f this x is equal to what is called x superscript k, kth iteration value, multiplied by delta f of x preceded, because this multiplied by delta. So, this is we call, this we have selected as a decay. So, this and put this value x is equal to x star, and this value always less than 0, because this is nothing but a f transpose of x into this quantity x is equal to x star x superscript k into delta f of x is equal to x star, and this quantity is less than 0. Note, however, if y is a, let us call y is a vector n cross n, agree this, then if you write it y transpose y is nothing but a scalar quantity, and this scalar quantity is always greater than 0. This means, if you see this one component y is nothing but a, if you wrote this one, if you just multiply, it is nothing but a y 1 square but y 2 square plus dot dot y n square is greater than 0, where y is a vector of dimension n cross n, its elements are y 1, y 2 dot dot y n. So, this is, and physically it is nothing but a distance square, agree, this is nothing but a distance square from the origin of this vector. So, this mathematically is, people are writing like this way, y norm of this 2 is nothing but a, this is the distance square, is nothing but a square root of y transpose y, agree. So, this quantity, if you see this quantity is a always positive quantity and preceded with minus. So, it is always this product of this one preceded with minus, it will be negative. So, if this condition is satisfied, in other words, if you consider the search direction decay with reverse sign of gradient of a that function, agree, then the function value from kth iteration to k plus 1 iteration, the function value will decrease, and you have to select the decay, the direction of this search vector direction, you have to choose that way. So, what is our choice of our search vector, search direction? Decay will be a minus delta f of x, that is our choice. So, okay, at decay, because at kth iteration. So, you write it this one k. So, decay is, I am writing once again. So, minus gradient of, find out the gradient at kth iteration, agree. So, that one, this is the direction, search vector direction you have to move next to go from x of superscript k, kth point to k plus 1 point, you have to move in such a way, so that function value is decreased when you move from kth point to k plus 1 point, and you have to move like this way, because function is known, gradient is known with sign, negative sign, reverse sign of that one. So, this way you have to move it. So, now so we will discuss, keeping this thing in mind, that how to select the search vector or direction vector, then we can proceed that how to solve a optimization problems, optimization problem of a function which is a n variable function by using this iterative process. So, our next is, we can say, the steepest descent method, and this is based on this what is called that concept. This concept will be used here. So, let us consider we have a function f of x, and x is a n variable. The function f is a function of n variable x 1 x 2 dot dot x n, agree, is to be minimized. That is our problem. So, you consider we have a sequence of point x of 0, x of 1, x of 2 dot dot x of k. This is the we have a sequence of point is generated. How it is generated? Using the following expression. Now, look at this expression, this one, our basic that concept what we consider is this one. That means, our problem is minimization. Now, if we are in kth point, agree, we move to k plus 1th point in such a way, in such a direction, so that the function value at kth iteration at kth point, the function value at kth point and the function value at k plus 1th point, that difference will be negative. So, that is the basic. With this thing in keep in mind, I can write a x k plus 1th iteration, that x of k, and which direction from kth iteration and from kth point, which direction I have to move in decay direction, and decay I know what is decay, minus of gradient of that function, this function. So, this is plus lambda k into decay. If you move in this direction, let us call you have a point is x k, x superscript a, you move in the direction decay, and decay was gradient of that vector, that function f of x with negative sign, you move that way. That's so you will get it x superscript of k. Then this value, at this value, the function value will be less than what is the value of the function at kth iteration. So, this is the expression, and this I told you this value is greater than 0, positive quantity, and this if you can choose the direction vector in such a way for all values of k, this is true, and also lambda k we have selected greater than 0, then ultimately we will reach to the what is called minimum value of the function. So, this method is called is called or known as the gradient method, because it is the whole this method that we are moving in such a direction, the function value is decreased from one point to another point. So, this method is called gradient method. With predetermined step size lambda k for each iteration. For each iteration, lambda k is predetermined and it is kept constant throughout the iterative process for each iteration. So, that is gradient method. Now, steepest descent method is just extension of gradient method. In this case, we have fixed the lambda k, which is nothing but a step size. We will move in decay direction, but what is the step size we will move it. Okay. Now, in steepest descent method, the lambda k is optimized. Lambda k means step size is optimized at each iteration. K is equal to let us call 0, k is equal to 1, k is equal to 2, k is equal to 3. In each iteration, lambda k is optimized. Step size of this one is optimized. Agree? So, this iteration, this is optimized, and then it is called, it is a steepest descent method. The difference between this and this only, this is the basic expression. Agree? So, this one, and this is the search direction, and the gradient method, the lambda k is predetermined, step size is predetermined, and each iteration it is taking the same value. Agree? Whereas, in the steepest descent method, the lambda k, that step size from one iteration to another iteration is optimized, and it is used to find out the value of decision variable at k plus 1th instant. This is the only difference. So, let us call in gradient method, one is what is called is a very simple gradient method is very simple, no doubt, but convergence is very slow. Gradient method is slow, very slow convergence, but easy to implement. Agree? But whereas in steepest descent method, it is simple, but little computation burden is increased when we are going to find out the step size of the lambda k optimally. So, that little computation burden is there, but convergence is fast, because we are each iteration we are finding out the what is called step size, optimal step size of lambda k in order to get the function value as minimum as possible. Because when you put this value in the function, it is a function of only single variable lambda k, because x of superscript k is known to us, dk is known to us. So, if you put this value that f of x k plus 1 value in this expression, and in this expression it is a function of lambda k only, and if it is a function is a that is a function is only a single variable case, we know how to find out the optimum value of function f of f, which is a function of lambda k only, we know how to find out its minimum value of this function. So, that way the convergence concept of convergence is more faster than the gradient method. So, and and you can see this one from x, that if you are at kth, if you are in the kth point, and if you move in the search direction, in the proper direction search direction, is slight perturbation in that direction, if you move it, there is a lot of improvement in the function value, meaning function value is decreasing. Agree? So, a vector which satisfy a vector dk. So, our conclusion, final conclusion is a vector dk that satisfies this condition. What this condition? Delta f, what is called gradient transform of this superscript k into dk if it is less than this 0, if a vector that satisfies this one, agree, is called direction of descent for the cost function. In short, if this condition is satisfied, then if you move from x k to x k superscript k plus 1, the function value will decrease at k plus k superscript k plus 1 instant. The function value will decrease from what is called function value at kth iteration or kth iteration function values. So, this is the condition, this is the important condition. So, so now question arises, how to find out the optimum step size of lambda k. Lambda k is equal to lambda k star, that means optimal step size. While we will go from k plus 1 to will go from k to k plus 1 at point iteration. Then what is the optimal size of that one? That means that one. What is the optimal size of that one? Lambda k. When you move from kth iteration to k plus 1th iteration, while we will update k plus 1 decision variables. How to move this one? So, let us see this one. And so, let us call it is a f of k plus lambda k. We move from kth iteration to k plus iteration dk. So, this nearly equal to, by Taylor series expansion, I can write f of superscript k this plus f transpose of superscript k of this gradient transpose this. And what is this one? I am just writing Taylor series expansion. This is lambda k into dk. This is the delta x, you can say delta x simply. Then half lambda k delta x transpose lambda k dk whole transpose. Then what is called gradient, that means Hessian matrix, differentiation of gradient of function, that function with respect to x once again. So, that is that one, that is why at what point, kth point value you this, and then lambda k dk, and I neglected the higher terms of this one. So, now you see this one, this is known to us. If you see, this quantity is known to us, known, this quantity also known, this quantity also known, this is also known, and this is also known, this whole thing is known, except unknown is here, unknown, lambda k, lambda k. Now, this is, if you see this one in this the function expression, if you put it that x k plus 1, that k plus 1th iteration, the value of x, if I put it here, the function is, that function, objective function or the cost function is a function of lambda k only. You see in this expression it is the lambda k only, lambda k. So, now what should be choice of lambda k, so that the function value is minimum for this expression. So, you have to differentiate this with respect to x. Since it is a function of single variable, I will write it d f, agree, which is a x of, okay, next page I am writing. This is nothing but a d f x of superscript k plus lambda k dk, that differentiate with respect to lambda k is assigned 0. This is a necessary condition for this one. So, I have to find out the function value is minimum for what choice of lambda, this is the necessary conditions. And if you solve this one, you will get the value of lambda. So, if you differentiate this one, you will see, if you differentiate this one with respect to lambda, this is a known constant. So, this will be 0, and this is what lambda k, differentiating with respect to lambda k, this is the, this vector is a row vector, this is a column vector, this is a scalar quantity. So, if differentiate this one, you will get same thing here. So, delta f transpose of f of k whole dk, this is the first term it will come, and this one you see lambda k is a scalar quantity, there are two lambda k's, lambda square will come, and it will be dk transpose the gradient, that is our Hessian matrix, then dk. So, it will be coming plus half 2, I am differentiating with respect to lambda. So, it is a lambda k, lambda square, lambda k square. So, the 2 is coming here, then it is a dk transpose, then Hessian matrix or second derivative of the partial derivative of the function. So, this f superscript k, this into dk is equal to 0. Agree? So, this is our necessary conditions. Then lambda k you find out, lambda k is equal to, if you just do this one, this cancel, lambda k is equal to, you will get, this is a scalar quantity, mind it, x transpose p x is the same thing, scalar quantity, and this is a also scalar. Agree? So, if you take it, this that side is a minus gradient transpose x of k dk divided by, I can divide because it is a scalar quantity, divided by dk transpose delta f square of x k into dk. So, you see this is scalar quantity, this is scalar quantity, and this quantity, the product of this one, I told you lambda k is greater than 0. So, this product, if you see this product, is a condition for descent direction. The function value will decrease from kth point to k plus 1th point if this product is negative. So, negative negative, here is preceded with negative. So, positive, lambda k is positive quantity. So, this is the choice of lambda k for which function value will decrease. If you take the lambda value, lambda k value, some other value other than this one, function value will decrease, but if you select this one, the function value will decrease as much as possible. Agree? So, this is the choice of optimum, this is the optimum step size. Agree? So, so this now we can check it whether the function value is optimum, just check whether this value is del square f x of superscript k plus lambda k dk differentiate with respect to d lambda k square, this value, putting lambda k is equal to lambda k star, that is we call this is equal to lambda k star. Okay. Put if this value is greater than 0, this is a scalar quantity, is greater than 0, that means function is value is decreasing as minimum as possible for the choice of lambda k. So, we will stop it today. Next we will continue with this one. We will write the what is called algorithm, then how to implement this one in digital computer for this one. Thank you.